If you have a pendulum, this is a pendulum, mass m, length L, then you can derive, which I do in class, but I won't bore you with that, you can derive how long it takes for the pendulum to make one complete oscillation. And we call that the period of the pendulum. And I derive in class that that period equals 2 pi times the square root of L over G. You already know what L is. If you don't know what pi is, you might as well leave right now. And G is what we call the gravitational acceleration, which is approximately the same everywhere on Earth, but it is very close in Boston to 9.80 meters per second per second. Pendulum that we have here is really the mother of all pendulums. Look at it. 15.5 kilograms, and the length of this pendulum is 5.21 meters. However, you must understand that it is very difficult. So now I can make a prediction. So I predict using this equation. That's all I do. I put in 5.21, I put in 9.80, I multiply by 2 pi, and I make the prediction that the period of that pendulum is 4.58 plus or minus 0.02 seconds. Why the plus or minus 0.02? Well, that is the 0.5% uncertainty due to the square root of L. And you can immediately see that 2 is about 0.5% of 458. So my prediction can be no better than that. I'm going to first make a period measurement at 5 degrees and then at 10 degrees amplitude. And I'm going to measure 10 periods, not 1. Some of you may think, well, isn't that a waste of time to do 10 periods if you can get away with 1? You will very quickly see why it is 10. You will see that. So the 10t is then going to be some number plus or minus my own inability, which is my 0.2 seconds reaction time. I can't change that. And so then I do it at 10 degrees, and then we get again 10t. We get a number, and then we get again plus or minus 0.2 seconds. And I'm going to demonstrate to you that within the uncertainty of the measurements, that I get the same numbers in all 3 cases, within the uncertainty. So, if you're ready for that, you see here the timer, all of you can see, and here you see the pendulum, and I have 2 marks on the floor here. If I hold the bulb here, then it is 5 degrees, this is 5 degrees, and when I hold the bulb here, it is 10 degrees. Timing is not easy. The best way to do it is to start the timing when the pendulum comes to a stop. That is rather well defined. And then you let it swing 10 times, and then when it comes to a stop, you stop it. And it would help me if you would count how many oscillations we have made. Because then I don't have to look at it. All I have to do is when I come close to 10, I have to watch for the moment of stopping, and then I will end it. So, we'll do this first at 5 degrees. I'm going to start it when it comes here. Yeah! Okay, now you count.
10,
45.7. So that becomes that t. That means this whole equation now has to be divided by 10. And now you will see why I measure 10 oscillations. So t is going to be 4.57 plus or minus 0.2 divided by 10. That is plus or minus 0.02 seconds. And you see, comfortably within the prediction. So maybe my reaction time is a little better than 0.2 of a second. Don't count on it because you haven't seen the rest yet. So, now 10 degrees. That moment is crucial. That moment is crucial. That's where you can lose 0.4 of a second and then you look like an idiot in front of your students.